So hi everyone. So I'm Andri Stefánsson, and I'm at the University of Iceland for those that don't know me. So today I'm going to talk about some other things than we have been hearing about today, and that is more how do we somehow fingerprint the signals of possible supercritical or super hot fluids. And in the roots or below conventional geothermal systems. So this is of course of interest to the industry and many of us for example, vectoring drilling and future utilization and so on. And we have been trying to move forward with this in the last few years, and we call it development and generation and application of something called second generation of geothermometry. And it's basically if we can somehow identify supercritical or super hot fluid input into conventional subcritical geothermal fluids. If we can see somehow look through the geothermal system that we are used to utilize and see what's below in a way, and if this is some kind of a supercritical or super hot fluid. And this all links to a phenomena that many of us call excess enthalpy well discharge behavior, which is a very technical term, but many boreholes that we drill and then discharge into these geothermal systems, they have too high vapor to liquid ratio relative to the assumption of a liquid reservoir at depth, and then adiabatic or closed system, or actually isolated system, boiling from the reservoir to the surface. And this excess enthalpy is a very common feature of many geothermal boreholes. And here I have shown two examples from the Helliseiði geothermal field and Nesjaveldi geothermal field, which are here southwest Iceland. And basically the data points that are sitting here above the, well, I'll find the laser pointer. This one-to-one line here, these are what we would call excess enthalpy of too much vapor in the discharge relative to this adiabatic boiling and liquid reservoir. So the cause of this, there are two ways of explaining this type of behavior. The first one is simply physics, that we have a depressurization boiling and phase separation in the, you can say in the conduit or in the upflow of the system. So basically with the steam phase or the vapor phase having a lower viscosity and density will just travel faster, whereas the boiled liquid will somehow get stuck on mineral surface grains. The other way of making so you can say this excess vapor is just conductive heating of the liquid in the reservoir by some external heat source, like a magmatic intrusion, for example, to form a vapor and eventually even a superheated or supercritical fluid. So we look at a simplified phase diagram of just pure water. It's upside down with zero pressure at the top here, and then following downward. So it's looking into the geothermal system. So the former thing, the depressurization, boiling and physical phase separation, that would be a process that is happening somewhere here in the two-phase field of liquid and vapor waters. Okay, and then the two phases separate on the way up to the surface. The other field would just be moving the heat content, just measured here as the enthalpy, from, you can say, a liquid phase sitting somewhere here towards through the two-phase region of liquid water and vapor, or if you're above the critical point of the system, just a single phase, you can say it's an expansion in a way, to form a supercritical fluid that would be defined somewhere here, or a super hot fluid that is more defined based on the saturated enthalpy of steam. So this would basically just be moving across here and boiling it towards here. And then we are always sitting at the surface and wondering if this excess vapor came from here or if it came from somewhere here. The way we're doing this is that we're trying to develop some kind of, we can say, a thermometer or thermometers in order to calculate the temperature of this excess vapor formation. And we have been doing two things, or trying out. And the first one is to look at the temperature-dependent volatility of non-reactive elements. This sounds a little bit maybe strange to many of you, but it's nothing to do with equilibrium like most of these geothermometers are about. They are temperature-dependent thermodynamic equilibria between a solid and a solute. But here we are thinking of the temperature-dependent volatility of an element that doesn't take part in such fluid-rock interactions. The other thing that we have been exploring is that many isotope fractionation reactions, they are very temperature-dependent. And they may be relatively quick at high temperatures or fast, whereas they are very slow or sluggish at lower temperatures. So we've been exploring the option if there are some isotope fractionation reactions that we can actually use that are kind of at equilibrium at supercritical conditions, and then they're kind of frozen at the subcritical conditions if the fluid from below is percolating through this upper part of the geothermal subcritical or conventional system. So I'm going to show you these two examples and just how they work with some examples from Iceland or application. And the first is to use chlorine and boron as the elements that are non-reactive. And these are the volatility of these two elements. They are kind of temperature dependent exactly in the range where we go from what we would call a conventional subcritical geothermal system towards something that we would call a supercritical or superheated or super hot fluid. So in terms of chlorine here, you can see here, if you would start with a reservoir fluid and you would boil it along the two-phase curve of water, the vapor phase would have very low concentrations of chlorine, and the boiled liquid will become slowly more and more concentrated. If you heat up such a reservoir fluid towards, you can say, supercritical temperatures, the chlorine eventually becomes volatile and enters quantitatively the vapor phase or supercritical phase. And the turnaround is maybe somewhere at these lower temperatures, somewhere between 350 and 450 degrees. For boron, we have more or less the same behavior. If we have low temperature boiling followed by phase separation, the vapor phase will be depleted in boron, whereas if we have conductive heat induced boiling to superheated to supercritical conditions, the boron will eventually just go all into this vapor or supercritical phase. And the turnaround temperature is somewhere between 350 and 350 degrees, somewhere there. And basically, we can turn these temperature-dependent volatilities of these two elements into temperature, knowing the total composition of a well discharge and its enthalpy. We can basically look at the boron and the chlorine content in the total well discharge and calculate what is the cause or potential cause and the respective temperature of the excess vapor in that particular discharge. I'm not going to show exactly how to do this because it's a kind of a a long iterative thing, but we can calculate based on this the vapor formation temperature in these excess boreholes, excess enthalpy boreholes, and we can compare it here with the reservoir temperature of the conventional exploited geothermal system. So we have here 3 Icelandic systems to see how this all work. Had to say I talked about before. Nesjavellir, both of these have many excess enthalpy boreholes, and then Krafla up in the northeast of Iceland, which display a very similar borehole behavior. And on the y-axis, you have the vapor formation temperature, and on the x-axis, we have the measured reservoir temperature within the boreholes. So what you can see here, and every single data point here represent a single measurement of a given borehole. So in total, these may be 40, 50 boreholes for the Helliseiði, maybe 25 for Nesjavellir, and roughly about 20, 30 for Krafla. And if the data are lying along the line or below the line, it means that you are having boiling and vapor formation within the reservoir itself, the typical, you can say, 250 to 300 geothermal reservoirs that you find in the within the system, or in the upflow zone of the geothermal system itself. If you have data points or calculated vapor formation temperature above this, these are potentially caused by this conductive heat transfer or boiling by a conductive heat transfer to the system. And if the temperatures are high enough, these could potentially represent supercritical or superheated conditions. And you can see here for Helliseiði, there are many excess enthalpy well discharges there, but almost all of them are caused by this phase separation boiling within the reservoir or the upflow zone. We go to the next system, and you can see that kind of part of the system has the same behavior, but now we are having boreholes that purely show input or signs of input of a much higher temperature vapor, possibly a superheated or supercritical fluid. And these are just normal boreholes with temperatures of 280 maybe degrees, like here in NJ23, but they are excess enthalpy wells. They have too much vapor, and the temperature of the vapor formation are maybe approaching or even exceeding the critical point of water. When we go to Krafla, we see that most of the wells actually have signs of such high temperature vapor inputs, and we know and have heard about the ITTP-1. That was the borehole that went into magma at 2.1 kilometers. This borehole eventually discharged 440 to 50 degrees single phase superheated vapor, and we are calculating based on the same thermometer here, roughly 510 degrees, so not so far away. So basically here we can see that in some cases that these excess enthalpy clearly show signs of presumably a deeper vapor phase that is percolating through the typical conventional geothermal reservoir and causing excess enthalpy behavior. And sometimes the temperatures are exceeding the critical temperature of water. So this is what we would call a supercritical fluid or super hot fluid. Okay, so let's go to the isotopes. So some isotope exchange reactions, they are fast at high temperatures and slow at low temperatures, like I mentioned before. And we can maybe use those to vector high temperature and deep fluids. And here I've showed you some examples. So here you have kind of the equilibrium time, the time it takes to reach equilibrium or 90% of equilibrium within the system. And this is basically just temperature here. And what you can see here are the typical somehow times in log years of the reservoir fluids in conventional geothermal systems, somewhere between years and hundreds of years. And these would be the corresponding fractionation rates in a way. So if we start here with water and hydrogen fractionation reaction, you can see that it's much faster than the geothermal fluid residence time, meaning that it'll just reach equilibrium at whatever temperature you are. Okay, so this is kind of too fast. Then you go to sulfur, sulfate, and sulfide, and it's kind of in between and possibly or intercepting with the residence times of the geothermal fluids. And then we go to CO2 and methane, and it's kind of slow. But you can see that at the higher temperatures, they are slowly approaching or intercepting the residence times of the fluids, meaning that they could possibly reach some kind of an isotope equilibria, and then you cool it in by a fluid flow into the geothermal reservoir, and the kinetics are much slower, so you won't have re-equilibration in a way. So if we have had a supercritical fluid that is sitting somewhere here that have possibly reached isotope equilibria, and then you put it into the overlying geothermal system, this fractionation could be somehow frozen in. And we have been trying all kinds of things. And the one that we are maybe focusing on today is called methane isotopologues or methane isotopes. It's actually measuring the relative distribution of all the masses of methane isotopologues that are of importance. And the way we do this is that this reaction is relatively fast, or this isotope exchange reaction is relatively fast at temperature above 350 degrees, and very slow at temperatures below 300 degrees. So within conventional geothermal or subcritical geothermal systems, this reaction or isotope exchange reaction is very slow, whereas within the presumably supercritical reservoirs, they can be much faster. So we have just going around that and analyzing this for all kinds of things, including these different isotopes, and then calculating the corresponding reservoir temperatures. And these are the results that we are seeing, and it's for the same systems as before, except we don't have for the Hellisheiði and Nesjavellir system I was talking about with the chlorine and the boron geothermometer. But here you have a comparison of a typical solute, like a quartz geothermometer, relative to the reservoir temperatures. And we are looking at, for example, the Krafla system, where the ITTP1 was here, Krafla 2 boreholes here. And these are boreholes that clearly showed some signs of a superheated or supercritical input into the conventional utilized geothermal fluid. But when we are looking at the classical solid geothermometer, we don't see anything like this because the re-equilibration is relatively fast. When you go to a classical gas geothermometers, well, sometimes we see things like this. We have excess temperatures of these gas thermometers, and these have often been interpreted based on excess flux of the gas or a sluggish reaction kinetics without any further explanations. But they are not so, it's more of a scatter than anything else. When you go into some of these isotope geothermometers, like the methane isotopologues, we see a completely different story. We are starting to pick up again, just like we saw with the boron and the chlorine, that there is definitely some high temperature vapor phase or a fluid phase equilibrium at temperatures of somewhere between 350 and 500 degrees. And then this fluid is basically mixed from below to the conventional overlying geothermal reservoir. The temperature drops to, let's say, 250 to 300 degrees, which is the reservoir temperatures of these utilized geothermal systems. And the fractionation or exchange of the isotopes within the methane are too slow to re-equilibrate. So the high temperature signals are somehow frozen in. And we are seeing this exactly with methane isotopologues together with the boron and the chlorine geothermometry temperatures, that they're pointing towards similar temperatures within similar systems. So to sum up, I mean, we are trying to somehow fingerprint deep supercritical fluids that are found below conventional geothermal systems by studying the well discharges at surface. And we are focusing on these excess enthalpy boreholes and trying to calculate the formation vapor temperatures if it's at the reservoir conditions in the upflow zone of the system, or if it's actually a deep high temperature vapor phase with temperature somewhere between 350, 500, 600 degrees. And we have been trying to apply this boron chlorine geothermometry with some success, at least for Icelandic systems, and then the same for methane isotopologue systematics. So in the future, we are hoping that slowly we develop more and better approaches to do this for other things, other elements, other isotopes maybe, or isotope systems, so we can start fingerprinting and possibly locating where to find such deep supercritical fluids in active geothermal systems. At least this is the approach, and we are using this as a part of the ITTP-3 project, trying to vector where to drill at the next location, which is Nesjavellir in southwest Iceland. So I'm going to stop here.
Thanks a lot, Andri. You have a few questions online, very interesting. Actually, it's very promising. I have a lot of questions for you, but first we start with, so Pat is asking if you looked at sulfate water isotopic system kinetics.
Yes. So we have looked at lots of things, and also and one of the things is carbon between CO2 and methane. One is sulfur and multiple sulfur isotopes between sulfide and sulfate. One is oxygen isotopes, and I think that's what you're referring to, Pat, oxygen between sulfate and water. And then we spent lots of time on this clumped methane isotopologues. But answering you, Pat, we tried sulfate water. It's kind of not working. But in theory, it may work. So maybe it's just our it's all the sulfur system, including the oxygen isotopes. They are really falling in this difficult zone of residence time versus re-equilibration temperatures. Okay, so it's not straightforward at all for the sulfur or oxygen isotopes.
No, definitely not. Yeah, that was about the oxygen isotope. There is another question as well. Where does H2O, sorry, where does SO2 H2O fall regarding the kinetics relative to H2S SO2?
Can you repeat this? Is this the SO2 water or it? Ah, okay.
Yes.
Okay, we haven't tried SO2. Okay, so yeah, we are doing SO4. So sulfate and sulfide, both the sulfur isotopes and oxygen. And I showed the sulfide in one of the slides. It's on the border of being too fast. Okay. Yeah. Okay. Yeah.
No, that's thanks a lot, Andri. It's very interesting, your calculation of the vapor temperature. And I'm really looking forward to hear more and discuss that more in detail with you, actually, because I can see a lot of places where that can be tested as well, where we have excess enthalpy in the fluid. So yeah, that's really interesting to try to see if we have a supercritical versus different just phase separation, depressurization. So yeah, very fascinating. I don't think there is more question directly for you.